In this video, we're going to cover section 1.7.1, kinetic and thermodynamic control of reactions. Now, we saw in the previous video on parallel reactions that we could estimate product distributions based on the relative magnitude of the rate constants responsible for those competing pathways. Now, one must be careful in using product distributions to estimate differences in free energies of activation, unless you are certain that the competing reactions are irreversible. That is, product distribution actually represents the relative magnitude of rate constants for product formation. However, if the product distribution changes over time, then the reactions are not irreversible. Those would be considered reversible reactions. And in these instances, the primary product isolated after a short time, this is said to be the product of kinetic or rate control of the product distribution, since the product isolated is one that is formed faster. Now, the other option is the product isolated after a longer time. This is said to be the product of thermodynamic or equilibrium control of product distribution, since it is the thermodynamically more stable product. However, thermodynamics and kinetics control all products, and sometimes these terms are thought to imply that temperature controls the reactions. In reality, the distinction between kinetic and thermodynamic control of product distributions is one of time and not of temperature control of the reaction. A higher temperature simply allows the equilibrium between two products to be established more rapidly. So let's look at an example of kinetic and thermodynamic control of reactions. So in practice, the product distribution of addition reactions, for example, this is dependent on temperature at which the reaction is performed. So you may recall from organic chemistry that if we have a diene in the presence of a hydrogen halide, that we will form two products. We'll form the 1,2 addition product, which is referred to as the 1,2 adduct, and the 1,4 addition product, which is referred to as the 1,4 adduct. And what we typically observe when we introduce this type of reaction is that at low temperature, we seem to observe a higher percentage of the 1,2 addition product. Whereas if we take that same reaction mixture and we increase the temperature to 40, 50 degrees, we see a reversal in the major product. That is, the 1,4 addition product becomes the more favored product at those temperatures. So we would call the product distribution which favors the 1,2 adduct as being under kinetic control, whereas the product distribution which favors the formation of the 1,4 adduct as being under thermodynamic control. Now, this free energy diagram helps to illustrate the competing pathways for what we call 1,2 and 1,4 addition. By comparing these pathways, we see that the 1,4 addition leads to a more stable product. That is, it has a lower delta G, while the 1,2 addition occurs more rapidly because it has a lower free energy of activation. So if you have a reaction where there's competing pathways, as in this example where we can form two different final products, if we're certain that the pathways are irreversible, then we would expect that the product distribution would not change during the course of the reaction. However, if one or both of those reactions are potentially reversible, then we expect that over time, we're going to form more of the thermodynamically favored product as opposed to the kinetically favored product. And the reason being is that when we carry out the reaction at low temperature, yes, due to the differences in the free energy of activation, the barriers between these two pathways, we would expect that we would form more of the 1,2 adduct. However, when we increase the temperature of the system, that's not only going to increase the probability that we can go over the larger energy pathway, but it also will allow the 1,2 adduct to reversibly go back to the intermediate and, in a sense, have a second attempt at forming the more stable, the thermodynamic product in this particular reaction. So again, with parallel reactions, if you're certain that the two paths are irreversible, then yes, you can use the magnitude of the rate constants to estimate the product distribution at any point during the course of that reaction. However, if by experiment you see that over time that product ratio is changing, then that's strong evidence that you have a reversible system. And in those situations, the thermodynamic product will always be the larger, more favored product at the end of the day, given time to reach that particular equilibrium state. So if you have any questions about kinetic and thermodynamic control and how it relates to parallel reactions and product distributions, by all means, send me an email. Thank you.